Oh. Mm. Hi, I'm Sahaja Priya. Our group number is 23. Now I'm going to give presentation on learning real-time ASTER path planner for unmanned air vehicle target sensing. Next slide. Introduction. Path planning is a critical function for mobile self-driving cars. The path planning problem is particularly complex for autonomous fixed wing aircraft since the aircraft dynamic restrictions such as minimum turning radius must be addressed throughout the planning process. The path planning procedure, aerial detection of ground-based objects complicates matters even further. Difficulty by requiring a downward-looking sensor's footprint to transfer across a set of targets. The path planning procedure must take into account not just the airplane dynamics, but also the shift of the sensor footprint while the aircraft travel along a predetermined path if the goals are met and are positioned far apart in relation to the vehicle's minimum turning radius. The path planning technique is simple, however, when the objectives are close together. Next slide. Cyprian, next slide.
This one?
Third one.
This one?
I'm not able to see.
No?
Yeah.
Yeah.
So the goal of study is to provide a path planning system for sensing a set of closely spaced objects that fully exploits the planning freedom given by the sensor footprint while functioning within the aircraft dynamic restrictions. The goal of the planning is to reduce the length of the journey necessary to observe all the goals. In this, the figure 1 depicts the problem which has 3 targets. In dealing with the issues of 3 technological issues must be handled in this case. Coupling of the route segments using the sensor footprint and determining the viewing order of the target. Each of these problems will be examined briefly. Next slide. Yeah. So with the numerous targets, the strategy entails devising an ideal path from beginning place to the first objective, then from the first target to the second target, and so on, until the targets have been visited. If the targets are widely spread relative to the vehicle's turning capabilities, this strategy works as well as long the ideal visit sequence can be defined. If the objectives are close together, coupling between the path segments owing to the vehicle dynamic constant must result in a negative outcome for the composite part. The detrimental consequence of this coupling is seen in figure 2, where an ideal approach to the first objective is designed. The vehicle direction as it files over the first target. So the majority of path planning methods generate pathways that pass directly over the targets of interest. These techniques are overly constrictive. Many downward-looking sensors used by UAVs have large sensor footprints. Viewing a target does not usually need flying right over top of it. Therefore, the direct route is avoided. Most path designers set flyover limit that do not take use of the range and flexibility. The sensor footprint provides the information that is advantage of being able to use the sensor footprint. In figure 3, it clearly shows that what happens when you look at a closely spaced objects. While enjoying, although a sensor with a large footprint is advantageous, it uses increase the complexity of the system. Path planning is really important. Next slide. Coming to discrete step paths, a successful route planning algorithm should provide a path that is not constrained by endpoints or headings, that makes full use of vehicle sensors, and that fulfills the vehicle dynamic restrictions. These capabilities can be supplied via discrete step pathways, which are constructed by joining simple turn and straight segment to build a flyable path. The decision of which primitive to utilize at each step is motivated not by traveling from point A to point B, but by achieving a set of specified path objectives such as sensing a group of targets. For this study, each basic segment is a discrete step path that has fixed length and is either a turn at the beginning or at the end of the path. Next slide. So in figure 4, It depicts a root tree with a depth of 3. It is intuitively obvious that shorter step length enhance the resolution of the path tree, and deeper trees allow longer pathways, increasing the tree's coverage area. Given that there is a finite number of nodes, there are practical restrictions to the growth of a tree, which expands exponentially with the depth of the tree. The depth of the tree is limited by a computer memory. As the step length and tree depth increase, affect the path planning, tree search speed, and the quality of the final path plan. Their importance will be explored further in the section 3, which describes the tree search. Taking everything into account, the easiest method for constructing the path uh, tree is to produce a fixed depth path tree. Next slide. Coming to LRTA A-star research, this study employs a unique application of the learning real-time A-star algorithm to determine which branch of a given path tree best achieves the intended path planning objectives. The LRT A-star algorithm is well known. However, it is traditionally been used for path planning. Issues with grid-based world 29 in general, the LRT A-star algorithm may be used in any situation. So grid tree directed graph or any other kind of the LRT A-star algorithm was chosen above the others. Quicker A-star method, since the path performance planners is limited by the amount of RAM required to hold the enlarged nodes. The use of LRT A-star increases execution speed and is sacrificed in order to lessen the search spatial complexity. Slide 8. Um, in LRT A-star algorithm is straightforward and elegant. Each node has a heuristic estimate of the remaining distance to go in order to fulfill the unfinished objectives. The current node calculates FC equal to KC plus HC, C at each stage of the search, where HC is the child heuristic estimate and KC is the cost of shifting to relevant child. In other words, FC is a projected remaining trip distance if KC is moved. The current node heuristic value is updated with H is equal to minimum of C, uh, and it then goes to the associated child. The search continues along the tree until either all the objectives are met or the path grows longer than the current optimal path, at which the search is terminated. Next slide. Um, so, uh, in LRT A-star search requires that H, H is always true for each node. The rationale for this criterion is straightforward. If a node on the optimum path overestimates the distance of the objective, the search may never reach that node and hence never locate it. The best the term heuristics refers to heuristics that estimate the real journey length, conservatively acceptable heuristics, and as well as determining appropriate beginning values of these heuristics that are required for LRT A-star search to function properly. It is allowed to initiate the search that would take a long time to learn the best path if the heuristics were set to 0. As a result, the first heuristic estimate should be as large as feasible while yet ensuring accuracy. Next slide. So terminating conditions. These are two extremes, however, may be combined to provide a termination condition that fosters continuous improvement of the path length while also allowing the algorithm to be terminated if no progress is made. This condition is to end the search if there has been no improvement in the path length uh, and for a certain number of iterations too. In other words, the search will last as long as the path exists. The length is increasing with the trade-off between the speed and path length performance becoming more favorable. The amount of non-improving iterations that must elapse before terminations is regulated here. The greater number of iterations necessary, the better the final route length may be. However, having a longer running time, this termination condition is successful because it is best. The trial is very easy to find. So the next slides are continued by Sai Priya.
Hello everyone. My name is Priya. I will continue the next search algorithms. Testing and comparisons of both LRTA and NILRT search algorithms. Um, Coming to the testing algorithms, I will test in two ways: in general testing and statistic analysis. Coming to these algorithms, we can check in 2000 target scenarios based on shortest amount of time, and these both algorithms will compared in these significantly faster than LRTA A star algorithm, and compared to the and computing platforms like different processor speed and memory capacity is compared to LRTA algorithm. And coming to the statistic analysis, tested in bimodal descriptions in different two model of conditions, and also biomodal distributions are split into a two modes, like Linus operating systems runnings and radiations of below targets is chosen. And coming to the next slide, these are the shortest and longest paths we'll take. This one is the longest one and this one is the shortest one path. LRTA search algorithm is running path and time length performance. It increases the stop size, and step size algorithm is running just slightly increase the length down of these parts. And coming to the testing shows, it will step size less than zero point 0.2 radians will measure these target scenarios algorithms. And coming to the LRTA search validations, LRTA A-star search validations like brute force global search based on Rubin's paths, and also directly over the dominated into ability to LRTA A-star search algorithms based on global search, and these are measured in a 0.5 percentage longer than another one brute force algorithms. And coming to the LRTA pinpoint largest scenario footprints, will take this footprint. It is a closely approximately to the and the brute force globally in such way this way, and it is also radius. It's between 1.1 is to ratio, and this one is LRTA utilize the largest procedure in this is 33% as a shortest path. And coming to the next slide, this is the path length of the LRTA and NILRT algorithms. These are two algorithms various step size. This means spectrum step sizes means 19 percentage of demonstrations and smaller than these 0.4 nodes. And coming to the next slide, this is a path length, and path length is a LRTA and NRTA. The various step sizes includes, and also this is a running time of the both algorithms. We have to compare in 0.2 radius, and this is not running times decreases in meanwhile. This algorithm depends on anthol based systems listed parentheses. And coming to these NRTR and increasing comparison systems like both algorithms in 10,000 iterations, no improvement taken around the 93 percentage of overall operating systems. This conclusion, like in both algorithms is optimal or near optimal path through both algorithms, like a solution to multiple and closely speed target and sensing algorithms. So the minimal length path is produced to same longer runtimes. And coming to the next topic, KNN LRTA simple solving pop of real-time algorithms. This means nearly neighbor nearly algorithms. We can take search the best possible ways to offline and hill climbing algorithms. Each sub goal sequences together with the associated with the goals of states and await the databases. And coming to the sub-goal database constructions, we have to see this diagram. This one is the Dörzler's LRTA search algorithm. It is a non-trivalent to has a bullet clinic abstractions, and this is also map of the mapping of abstraction of PRP. Coming to the next, running time for the NLRTA. NLRTA algorithm is indexing mappings. It's a running time, and which consumes the sub goal will be obtained, and also heuristical distances is predictably determine the functions, and it's greatly similar to index mappings, and also hill climbing will apply the ALRTA search algorithms, and the sub goal will be attended. Coming to the exporatical evaluations, exporatical evaluations is the outcome drawn from the rather theory of experimentals, and limited best solutions were the found, and particularly between 100 to 150, we have to give an average of 1024 distance pathfinding search algorithms. These are heuristically valid the web-based OLBs, and this is the database size, number of states, expansions per move. These are the different types of algorithms we have to do this, and this is the KNLRT and KNL number of iterations based on these algorithms, and database sizes is started ration map page, and database consumes the RAM and the map. Coming to the next one, the conclusion is DLRTA is the high performance real runtime appropriately video games has been developed, and similarly implemented the DLRT algorithms, and the KNN LRTA star algorithms is a strong storing the sub goal databases, and AI algorithms they based on simple to build a small memory footage and performances. um yeah, yeah, thank you.
Thank you.
Yeah.